Let's talk about Young's double-slit experiment. So here you can see a fully worked out example with the diagrams and the calculations that would go into solving a problem from the double-slit experiment. But let's first talk about what the experiment is and why it was important in the history of science. So in the 1600s, there was a debate. You got Isaac Newton on one side, you got Christian Huygens on the other side. Isaac Newton is saying light is a particle, Christian Huygens is saying light is a wave. Okay? And it wasn't until the 1800s, 200 years later, that they started to unravel this mystery. And when they did unravel it, they started to discover in the late 1800s into the early 1900s that light is both a particle and a wave. Light has properties of both particles and properties of waves. Light is composed of photons, which are light particles that contain a wave packet of energy. And light has wave-particle duality, which is an expression we're going to talk about a lot in this course. So that's what we know today, but we didn't know that back in the 1800s. And experiments were being developed to determine, was light a wave, was light a particle? And the most famous of these was Young's double-slit experiment. And what he asked was, if you passed a light source through a double slit, which is just an opaque surface with two slits cut into it, what would you see on the other side? And he said, if you had a light being a particle, then you'd see something very different than if light was a wave. If light was a particle, then the beam of particles would go through those two slits, and what you would see on the other side are these two bright spots, these two areas where you have lots of light particles hitting the screen, and you would see these two lines, right? But if light was a wave, you'd see something very different. So what would we see if light was a wave? Let's take a look at an experiment from the University of Colorado. And what we are going to see in this simulation here is light going through just a single slit, right? If light goes through only a single slit, then what you have are these spherical wave particles, or spherical wave patterns that emanate outwards from that single source. And we're going to talk about that coming up. But if light was a wave, then what if you had two of these slits? If you had two slits, then you'd have two sources of light, two sources of spherical waves, and the waves would interfere. So imagine that you had a pond, right? And imagine that there were ducks on the pond. So in this simulation, this one source over here represents one duck, and this source over here represents another duck, right? And if the two ducks were making ripples on the pond, then you would see these circular wave fronts traveling outwards and then interfering with each other. Waves interfere, right? Constructive interference occurs when you have a crest meeting another crest. Destructive interference occurs when you have a crest meeting a trough. And you can see that on the viewing screen over here. You've got where there's a crest meeting a crest, you have constructive interference, a bright spot. Where a crest meets a trough, you've got a dark spot for destructive interference, bright spot, dark spot, bright spot, dark spot. And that's what you would expect to see if you had light being a wave. So if we go back to our experiment, that is exactly what was observed. Light had this wave-like property where this pattern of bright, dark was seen on the viewing screen. And this was seen as a very strong case that light was, in fact, a wave. Leave it to Einstein in 1905 when he published his paper on the photoelectric effect to show that light actually behaved more like a particle in some respects than it did as a wave. So we're going to talk about that coming up. But for now, a typical problem would involve, given a certain wavelength of light and given a certain slit spacing d between the two slits, and given the viewing distance L from the slits to the screen, find the distance from the central maximum, and here you can see the central maximum, to one of the bright fringes. Because you can see there's bright fringe number 1, bright fringe number 2, and you can have bright fringes going, many numbers out. So 3, 4, 5, 6, 7. So that's going to be a typical problem that we're going to take a look at. So let's look at the underlying theory and develop a model for how we can calculate what we need to calculate in these problems. So taking a look at our notes, we're going to start with a derivation for the equations for the double-slit experiment. Okay? In order to do this derivation, we have to start with a picture, right? Please draw this diagram that we have here, where the two slits are the sources of spherical wave fronts. Okay? So let's start out by drawing the barrier, the opaque barrier. Opaque means that you can't shine light through it, with the two small slits cut into it. Okay? So the light is shining in from this side over here in these, parallel wavefronts, almost like waves, crashing against a barrier at the beach. And then according to the simulation, we see that these slits act as point sources for concentric spherical circles, or concentric spherical wavelets of waves. And this, by the way, is known as Huygens Principle. Huygens Principle states that every point on a wavefront, so for example, this point here, as it passes through the slit, is itself the source of spherical wavelets. So when the light passes through, the light wave that passes through is the source of spherical wavelets that emanate outwards. Okay? Let's do a couple more of these for this wave. And for this over here, we'll do the same exact thing. Now this diagram is very difficult to draw, but I invite you and encourage you to try your absolute best. Okay, I have a lot of practice drawing this diagram because I've done it several times. But as you can see, all I'm doing is drawing concentric circles. Okay, I'll do one more for good measure. Okay, now, in order to unpack this, we're going to want to define a new quantity. Okay, this new quantity is called the path difference. This is going to turn out to be very, very important. The path difference is delta L. Okay, L is the distance from this point or this point to a location of constructive interference. Okay, so let's pick a random point where we have constructive interference. So let's say that at this point right here, you would agree that we have constructive interference because we have the wave front crest of one wave meeting the crest of another wave. So this would be a location of constructive interference. So I'm going to put a little key here. This is going to represent constructive interference. And the path difference, delta L, will be the difference between the lengths of the paths to a point of constructive interference. So what do I mean by that? Well, to get from this point source to the constructive interference, how far do we go? Well, we go 1, 2, 3, 4, 5 of these wavelengths. Because remember, the distance between the crests of the wave is the wavelength. So this represents 1, 2, 3, 4, 5 lambda. So I'm going to write 5 lambda, because this distance is 5 lambda. So you can see lambda there. Okay. What about from the other wave? We would go 1, 2, 3, 4, 5, 6, 7, 8, 9 lambda to get to a point of constructive interference. That'll be 9 lambda. Okay. But I picked that point arbitrarily. What if I had picked a different point? What about this point over here? Maybe this point, right there. Let's see. So we're going 1, 2, 3, 4, 5, 6, 7 lambda. This is 7 lambda here. And then we're going 1, 2, 3, 4, 5, 6, 7, 8, 9 lambda here. So that's 9 lambda. So what can we say about the path difference? Well, delta L is going to be equal to L2 minus L1. That's just the difference in those path lengths. So 9 lambda minus 5 lambda for the first point, 9 lambda minus 5 lambda would be 4, oops, I ran out of space, equals 4 lambda, right? Well, what about the next one? The other delta L was, this was 9 minus 7, so 9 lambda minus 7 lambda equals 2 lambda. So we had 4 lambda, then we had 2 lambda. Do you notice a pattern here? No matter where we pick our point of constructive interference, and just to illustrate this, let me pick maybe this point right, say I pick this point right here. Right? Now we got 1, 2, 3, 4, 5, 6 lambda versus 1, 2, 3, 4, 5, 6, 7, 8, 9 lambda. 6 from 9, that's 3 lambda. So delta L in that case would be 9 lambda minus 6 lambda is equal to 3 lambda. Now what do you notice? We went 4 lambda, 2 lambda, 3 lambda. what do all of these numbers, 4, 2, and 3, have in common? This was the major insight that led to the development of the theory here. That delta L, this change in path length, is always a blank multiple of the wavelength lambda. No matter where we pick this red dot, which has to be a location of constructive interference where a crest meets a crest, it's always going to be an integer multiple of the wavelength lambda, okay? And this is the major conceptual takeaway from this diagram, is that delta L, the path difference, is always an integer multiple of the wavelength lambda, okay? So we're going to take this with us going forward into the next part of the derivation, okay? So if we know that delta L is always an integer multiple of the wavelength lambda, then we can say that delta L is equal to m lambda, where m is equal to, it could be 0, 0 is an integer, it could be 1, it could be 2, it could be 3, dot, 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 right? And it could be a positive number, it could be a negative number, but it just represents an integer, right? So this here is a very important relationship between delta L, the path difference, the wavelength, and this integer m, okay? Very nice. So we're going to take this a step further, okay? We're not quite done. Now what I would like us to do is to draw another important diagram. And I got to tell you, this is arguably the most important diagram in the whole derivation, okay? We're going to zoom in now, and we're going to look at this double slit. So here is the double slit here. Okay, we're going to do some amazing geometry, okay? Now, again, this distance d is the distance between the slits, okay? So that's called the slit spacing. So down here I'm going to write d equals the slit spacing, okay? And what we're going to say is that let's imagine that there's some point in space very far away, okay, where we have our point of constructive interference. Now, this slit spacing is very, very small. We're talking about less than a millimeter, okay? So this distance is very, very small compared to the horizontal distance scale, okay? So imagine that at some point very far away, we're going to have a location of constructive interference, okay? So what I'm going to do is I'm going to draw the rays of light associated with that constructive interference, okay? So this is one ray here, and this is going to be another ray here. And these two rays somewhere are going to meet up. And you can imagine, if we take the limit where this horizontal distance is very, very much bigger than this little distance for the slit spacing, so let's call capital L this very comparatively large distance. Capital L is going to be the distance to the viewing screen. So the distance to the screen in the limit that L is bigger than the slit spacing. So this notation means bigger than is much, much bigger than. In the limit that this L is much bigger than this slit spacing, then what can we conclude about these two rays? If they're going to meet up somewhere very, very far away, then you can argue that if this first ray is at some angle theta with the horizontal, then this other ray is also going to be at the same angle theta. And again, this is making the assumption that the viewing screen is infinitely far away compared to the very, very small slit spacing. Okay? So, we've got these two rays that are going to meet up somewhere in space, very far, far away. Okay? Now, this first ray is going to be of length, let's call this L1. And this second ray is going to have length L2. Now the question is, which ray is going to be longer if they're going to meet up in space somewhere? if you said that L2 would be longer, you're absolutely right. And you can see that they share most of the same length, don't they? But there's a little difference. This L2 has this extra little distance down here, doesn't it? So what we're going to do is we're going to draw a normal to L2 as follows. You ready? We're going to draw a normal to L2 like this. You see how I drew that normal? So that's going to be a 90-degree angle right here. And here we've got the slit spacing D. And let me ask you a question. If I wanted to identify what this length down here is, if I wanted to identify what this little piece down here is, let me ask you this. Where have you seen this little piece earlier in our derivation? L1 is the distance from this slit to the constructive interference. L2 is that distance. So then this distance here, this little leg, must be what? It must be the path difference, right? The path difference, delta L. The difference between the lengths of the paths to a point of constructive interference. So that little distance right here, we're going to call delta L. So I'm going to write this down here, delta L. So this distance down here is delta L, okay? Now, one more thing, a little bit of geometry. If you know that this angle is complementary to this angle over here, and if you know that this, and let me call this angle phi, okay? I got to give it a name. I'm going to call it phi. Let me use a different color, okay? I'm going to call this little angle phi. Okay? If I know that the angle theta is complementary to the angle phi, and how do I know that? Because the horizontal is perpendicular to the vertical, right? So that means that theta plus phi has to be 90 degrees. And if I know that this is a right triangle in here, right? Because I chose a normal to L2, this green line forms the height, you could say, of this right triangle. And because this angle is 90 degrees, the other two angles have to add up to 90 degrees in a right triangle. So this angle has to add up to 90 degrees. So if theta is complementary to phi, and phi is complementary to this angle here, then by the transitive property of geometry, that means that this angle is also theta. In other words, if theta plus phi equals 90, and this angle plus phi has to also equal 90, then this angle theta has to be the same as that angle theta. Okay? So we've just proved that we have this little triangle in here, and I'm going to zoom in now on this triangle because there's something very special happening inside this triangle. So the slit spacing is D. I'm going to draw that over here. This distance is D. I've got the angle theta, and I've got this delta L down here. So here's my delta L, and here's my normal. Okay, so this is delta L, and this angle here is theta. Okay, so ask yourself, which trigonometric relationship is going to relate theta, D, and delta L? If you said that D is the hypotenuse of this triangle and delta L is opposite to the angle theta, and therefore we have to use the sine function, you'd be absolutely right. So we're going to say that the sine of the angle theta is going to be equal to opposite over hypotenuse, so delta L over D, and therefore delta L equals D sine theta. Okay, let's put a rectangle around this. Okay, maybe you see where we're going now. We've got a delta L equals m lambda, where m is an integer. We've got delta L equals D sine theta. What are we going to do? If we've got two different equations with the same quantity, one of our favorite things to do is to set these two things equal to each other. And that's exactly what we're going to do. And that is going to yield, drum roll please, the condition. This is a big deal. This is the condition for bright fringes. When we say bright fringes, we're talking about constructive interference. Because where a crest meets a crest, you're going to have a bright spot, and that's going to be a constructive interference. And we have just derived the following relationship. If delta L equals m lambda, where m is equal to 0 plus or minus 1 plus or minus 2 dot dot dot, and delta L also equals d sine theta, well then I think you know what we're going to do. We're going to set these things equal to each other, and we're going to get m lambda equals d sine theta, where m equals 0 plus or minus 1 plus or minus 2 dot dot dot. And this is a big deal. So I would star this, I would put a smiley face next to it to indicate how important this is. This is one of the equations that we need to solve the double-slit experiment problems. So let's now look a little bit more zoomed out. And I want to really focus on this angle theta for a moment. The angle theta can be defined as the angle that produces the mth, it could be the first, second, third, the mth bright fringe. Okay? So now what we want to do is we want to take this picture that we drew earlier and we want to really zoom out. We want to zoom out so far that we can actually see the fringes on the screen. Okay? So to do that, we're going to draw another diagram, and this will be the last diagram, where we're going to say, okay, so here's our double slit. You can see that I've zoomed out. Now the slit is much smaller on my paper. But more importantly, I've got this principal axis, this central axis, and on the central axis, I'm going to put a viewing screen. So here is going to be my screen, right here. Okay? Now, what we saw in the simulation and what we see with experiment is that on the screen, we're going to have a central maximum, okay, where the crest meets a crest right in the middle where the path length is exactly, or I should say the path difference is exactly 0. So this represents where the path difference is 0. And remember, delta L, we said, was equal to m lambda. So if m is equal to 0, then this is going to represent this central maximum. Okay, so this is going to represent m equals 0. So I'm going to pick this color. I'm going to say this is m equals 0 right here. Okay, now what about our next bright spot? Our next bright spot will be up here. Okay, and this is going to represent m equals 1. The next bright spot is going to be up here. This is going to be m equals 2. Well, by symmetry, we also have to have bright spots down here. So this is going to be m equals -1 and m equals -2. And by symmetry, whatever distances we have above this central axis have to be the same distances below the central axis. Okay? So let's say we're looking for the second bright spot. So this m equals 2 represents the second bright fringe. All right, so now when the light rays come through the point sources at the double slit, we've got that angle theta, and the two rays are going to meet up at this point in space and produce that bright fringe. So that represents the angle theta right there. Okay. Now we defined earlier this distance L. L is the distance to the viewing screen. Okay, so L equals distance to the screen. All right. So now look at this. We've got an angle theta. We've got a distance L, and what we want to solve for is this distance y. And y is very important. Y is the distance from the central max, that's the m equals 0 point right there, to the mth You know, it could be the first, second, third, whatever, the mth bright fringe. Now, if you ask yourself, what is the mathematical relationship between the viewing length L, the angle theta, and the distance y? Well, it's a right triangle, right? Because we know that the horizontal axis is perpendicular to the vertical axis. So that means that we can use a trig function to relate these quantities. Now, if we have an angle theta, we don't have the hypotenuse here, but we do have the sides, so let's use the tangent function. We're going to set up the tangent function by saying the tangent of the angle theta is equal to the opposite over the adjacent, so y over L. And this can be rewritten in a more familiar form of y equals L tangent of theta. And this is another super duper important equation that we derive in order to solve these problems. Okay? So notice that so far we've gotten two major equations. Y equals L tangent theta, and we've got m lambda equals d sine theta with m equals 0, 1, 2, okay, etc. So we're now ready. We're now equipped to solve any problem that somebody could throw at us using the double-slit experiment. Okay? So let's look at an example now. In this example, we've got monochromatic light, and monochromatic means one color. So this could be red light, could be blue light, could be purple, we don't know. Actually, that's what we're trying to solve for in this problem. So monochromatic light passes through a double slit spaced 0.275 millimeters apart. So let's start to set this up. So we're going to say given, and if you need to pause the video to write the example down, feel free to do that. So given, the slit spacing D is 0.275 millimeters. Now, I like to unpack the milli by writing times 10 to the negative third meters. Okay? That's the distance between the two slits. So that's the slit spacing D. A viewing screen is 0.55 meters away. So that's going to be our capital L. So capital L is 0.55 meters. The second maximum is 1.8 millimeters away from the central fringe. Now, if we go back to this diagram, when they say that the second maximum is a distance away, well, that's the distance y. So therefore, we're going to say y here is equal to 1.8 millimeters, and milli is times 10 to the negative third meters. Okay? And we want to find lambda. So the question is lambda equals question mark. This is the problem that we want to solve. So in order to set this up, let's look at our two equations. First of all, we had m lambda equals d sine theta. Now, we're trying to find lambda. We're trying to find the wavelength of the light. We know d, but we don't know theta. Do we know m? Well, m is the number of the fringe we're looking for. Guess what? The number is 2. So that means that we have 2 times lambda equals d. I'm going to substitute this in. It's all SI units here, so I'm just going to put the numbers. So 0.275 times 10 to the negative third times sine theta. So if we knew theta, we could now back solve to get lambda, right? Well, how do we solve for lambda? Well, we derived another equation, didn't we? Over here. Y equals L tangent of theta. So we're going to say, okay, y is equal to L tangent theta, which means that this distance y, which is 1.8 times 10 to the negative third, is L, which is 0.55, times tangent of theta. Okay, so let's solve for theta next. So solving this equation, I'm going to rewrite the equation. 1.8 times 10 to the negative third equals 0.55 tangent of theta. If I solve this for theta, I'm going to get theta equals tangent inverse of 1.8 times 10 to the negative third divided by 0.55. Right? Because we divide by 0.55 and then take the tangent inverse to get theta by itself. And if you calculate this, when I solved this problem, I got theta equals 0.1875 degrees, okay? And that's a very small angle, but we're not surprised because when we show this on a screen, these distances are very, very small. I mean, look at this. The distance to the second fringe was just over a millimeter, just slightly bigger than a millimeter. Very, very small distances, so we're not surprised to see a very small angle there. All right? Now, the next thing we want to do is take this theta and plug it into the equation that we developed. 2 lambda equals 0.275 times 10 to the negative third sine theta. We're going to take this angle and plug it in for theta there. So for lambda, we're going to get 0.275 times 10 to the negative third times sine of 0.1875 degrees divided by 2. And when I solve this, I got 4.5 times 10 to the negative 7th meters. Now this is a very awkward way to write a distance. The best way to write distances at this scale is in nanometers. Okay? So we're going to convert this into 10 to the negative 9th. So to make 10 to the negative 9th, we have to go down by a factor of 100. So we have to make this bigger by a factor of 100. So we're going to move the decimal place 2 times over to the right. We're going to get 450 times 10 to the negative 9th meters, or 450 nanometers. And 450 nanometers is associated with blue light. So the light that was passed through this double slit must have been blue light. All right, and that completes our example. Now, notice that in our example, we kind of worked backwards, didn't we? Because rather than starting with lambda, we backed into lambda. Now, it could go in different directions. They might ask you to solve, for example, for y. They might ask you to solve for the slit spacing d. They could even ask you to solve for the viewing length L. There's a lot of different ways to set up this problem. So there's an introduction to how to solve these problems. I wish you great success and great luck solving these problems.